Okay, AP Calculus, back with another video. This is the final one in our series with finding limits analytically. Now we're going to look at our trig identities. So there were a couple of limits that were in the book that were given to you as defined limits. So we're going to jump into those and see how we use some trig identities to help get those limits analytically. Okay, so I'm now looking at, and I put up here at the top, these two, which were given to you in your book. Now, the way that these were determined was by using the squeeze theorem, but you can also, again, determine those limits you can determine those limits numerically and graphically. So we had limit as x approaches 0 of sine of x over x is equal to 1, and then you have here limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. So in the book, they used a squeeze theorem to kind of prove that analytically, but you can also prove that those limits are the numbers using numerical values and also using graphs. It's probably easiest to see it by just graphing the function. I will point out that from whenever we are using trig functions with calculus, because this is the first time we're seeing these trig functions here, whenever we do trig with calculus, you must always be in radians. Your calculator should be forever set to radians. Do not change it from radians. It will never be in degrees, always radians, okay? So how do we use these identities or these limit definitions in order to solve further ones? So here in my first example, I have sine of 5x over x equals, so I can see already through direct substitution that this would be an indeterminate form. If I were to directly plug in 0, I'm going to get 0 over 0, which is an indeterminate form. So that indicates to me something can be removed. But unlike the ones that we did in the last video, I don't really see any sort of algebra that I could do right out of the gate to kind of cancel things away for it to be, solvable and for me to be able to plug in the number directly. So this is where we come back and we kind of think about this. Well, I already know that this is true. How can I apply this here? So the first thing you want to remember is that the x is a variable. X can represent anything. So when I look at this, I'm looking is at this chunk right here. It would be really nice if this bottom part here was exactly the same as this. Because what this is telling me is that sine of something over that same something, if we're going to 0, is equal to 1. So right now, this and this are not the same something. How can I make it be the same something? Well, this is where now some algebra techniques come in. Well, if I could multiply this by 5, then it would be both the same. But I can't just multiply one side of the fraction. I have to multiply both sides of the fraction. So that's what we're going to do. We're going to multiply both the top and the bottom by 5. So that bottom part and the top part. So by doing that, and again, I'm always rewriting the whole limit. Don't just write the body of the limit. You need to write the limit approaches 0 at the front as well. So now I got 5 sine 5x over 5x. So now we can see, there we go, sine of something over the same something. So according to my limit that I got earlier, I know that this, when we approach 0, this will approach 1. And now I have that 5 left over, so this is really going to be 5 times 1, which is 5. Now, we saw the answer is 5. what would be an incorrect, so we can, some of you might have looked at this and said, well, why don't I can get 5 if I just cancel out the x's. Isn't that the same answer? No. You got the right answer, but for the wrong reason. So this is why it is important to know how to do it correctly algebraically, because it's not just about getting the right answer, it's about how we get to the answer. So doing it that way would, well, you get the right number, it's not going to give you the right solution in terms of the steps to get there. All right, so let me go ahead and erase that so we don't get confused to think that that's the right way to do it. All right, so let's look at our second example. So down here I have sine squared x over x. So again, we might be tempted to look and go, well, that's almost like that. So it's going to be 1, right? Again, if I were to directly substitute, I'm going to get my indeterminate form, meaning something can be removed. Okay, so I know that sine squared is the same as saying sine of x times sine of x. So I'm going to start there. So here's the thing, remember from trig, is that there are a number of different ways that we can rewrite trig expressions. So try all those different ways. So when I first said, what is sine squared? Some of you at home might have been thinking, well, 1 minus cosine squared, because it's a Pythagorean identity. Or it's 1 over cosecant squared, because it's a reciprocal. There are so many different ways to rewrite it. So sometimes the first identity you might use may not work. Try different things. Okay, you may not get it right out of the gate in the first shot, so try those other identities. Okay, so just kind of like don't give up if the first one doesn't work for you. So I have this, so now I can see, oh, perfect. I got that identity happening right here, sine of x over x. I know that as we approach 0, this chunk here is going to approach 1 because of my identity from above. So I really have, this is going to become 1, this part here, and now I have is this part that's left over. Well, what happens as x approaches 0 for sine of x? Well, that will approach 0. So my answer would be 0 times 1, which is 0. So again, initially, when I stared at this, you may have thought, oh, this is just going to also be equal to 1, because it's fine, it's squared, but 1 squared is 1, so yeah, but the top was squaring, not the bottom. So this is where now the answer would have been 0. And again, we can confirm this by doing it, we could be doing it graphically, we can be doing it numerically, but we know that those techniques, if I don't have a graphing calculator, it might be difficult to do. So this is why we practice doing it, analytically and learning these different techniques. All right, now let's look at our third example here. So now we got ourselves a little bit of a messy one here. So we have limit as x approaches pi over 4 of 1 minus tangent of x over sine of x minus cosine of x. Okay, no squared trig functions here. I really don't see that other limit function happening here. So how do I go about approaching this? Well, we could start by getting, one less trig function, because right now I see I have 1, 2, 3 different trig functions, but I know I can rewrite tangent as sine over cosine. So that's where I'm going to start with my trying to simplify this. And again, I know that maybe something can be removed, because if you were to directly substitute pi over 4 in here, you would see that we're going to get that 0 over 0 indeterminate form to appear. So this is why I'm going through that process. So remember, always first try to directly substitute to see if maybe it's continuous at that point. Don't dive into, let me simplify expression, because you might be doing all that work for nothing because it's already continuous at that point. So here I'm going to rewrite tangent as sine over cosine. All right, and then we got sine minus cosine. Okay, so now I have fraction within a fraction. So it's looking more, it looks messier than what it had before. Messy is good. That means that gives us more things to work with. However, it's a little bit simpler because now I don't have 3 different trig functions. I'm now down to just having 2 different trig functions, sine and cosine. Okay, so what I'm going to do next is let's put these together because I want to combine fractions. So I have the 1 minus sine over cosine. So we want a common denominator. So this will now become cosine minus sine over cosine. So that's my numerator. The denominator still is sine minus cosine. So all I did, and again, I'm putting that pi over 4 in here. So all I did from this step to this step was, okay, I combined the numerator, so I have a single fraction. All right, next step, we'll go ahead and just put this so that it's one fraction, not a compound fraction. So now it's going to say limit x approaches pi over 4, and now we have cosine x minus sine x over cosine sine minus cosine. So now we have a proper looking fraction. Okay, can we now remove anything? Yeah, we can remove this and this. So we can remove this and this since they are the same, but their signs are different. So when we remove those, it's not just going to disappear and turn into 1. It's going to turn into a negative 1. So limit x approaches pi over 4 of negative 1 over cosine x. Now I have removed the discontinuity. Since these two were the same, the only difference was the signs, it turns into that negative 1. Okay? So now I have this, which is continuous at pi over 4. So if now we substitute in pi over 4, we will get negative 1 over, made it too small there, sorry, square root of 2 over 2, which is just going to be a negative square root of 2. So that would give me my answer. Let me move this over here so my head's not blocking it. So now you can see. So now we have that. This didn't involve having us to use any of the 2 previously defined limits, but we did use trig and trig identities to help kind of break this down further. Okay, so there are a couple of more variations of the first example that you'll run into the problem set, but you want to use that same technique to help you kind of evaluate those. And again, you can always verify your answers by doing it using the other 2 techniques of looking at it graphically and to look at it numerically by plugging it in. All right, so that does it for our series on solving limits analytically. If you've liked these videos, please make sure to hit the like button, subscribe to the channel so you get updates on when new videos are coming out, and I will see you guys in the next one.